Hey guys, thanks for coming to our first talk. And basically, we have a UQ lecturer, Dr. Shekhar Chandra, and he'll be basically explaining how he's using AI in the medical imaging. So I'll let him take over. The floor's all yours.
All right. Thank you, Utkarsh. Thanks to the committee for having me here. It's a pleasure to be here. I'm Shakes. I'm a senior lecturer here at UQ, and I teach computer science, pattern recognition, and I'm a researcher in medical image analysis. So today, I wanted to talk about AI and ML in medical imaging, specifically um, going into three parts today. I wanted to talk about why AI and ML. Is it a revolution or a hype? Hopefully I can convince you that it's a revolution. Obviously I might be preaching to the converted, but um, hopefully you will see that maybe some new ideas of why this AI ML revolution is worth considering, even if you were a fan to begin with. The second part is just a quick introduction of how we use ML for imaging, especially with newer technologies such as deep learning. And then I'll get into the stuff that my team and I are currently doing here at UQ. So the first thing is it a revolution or is it just overhyped? So the stuff that you're probably using right now, live transcribing, digital assistants, those are all, provided by all of these big companies, but they are tangible AI sort of related technologies that you're probably using. So I wanted to start off by showing you this particular photograph of a human face. Now, usually it's not a good idea just to show faces of someone other than yourself. But why I can do this quite confidently is because this person doesn't actually exist. So there are AI algorithms, generative adversarial networks, in this particular case, the StyleGAN2, which is designed to generate these faces from scratch. In fact, they're completely randomized and the people don't exist. So that's the website you can have a look at. I'm not going to fire it up, but every time you load that page, you'll get a new distinct face. And of course, that utilizes this machine and deep learning that we're going to be talking about. So here are some other examples of such things. You can have these AI technologies learn the relationships between text and images. And there's an example there, and it goes on to show some other examples. But also, you can use it to put things into the designer, and the designer will, generate something for you. And these are all based on this latest technology called GPT-3. I'm not going to talk about it in detail, but we will see what it's called and what sort of technology it really is. So most of these technologies are actually based around neural networks. So just quickly going through what neural networks are. Firstly, the neuron, and you can think of it basically as a very advanced, well, not really advanced, but a generalized glorified switch. So you have multiple inputs, weighted inputs. And if you can see my pointer, it's basically these inputs here, K0, W0, K1, W1, etc. And the weights are important, and we'll get to. But it's basically, you take the weighted sum plus some offset, and you pass it through an activation function, which we'll talk about later, and you make a decision to whether to fire or not. And that's all it is. And what we do is we actually form a network out of these. And so you'd have an input layer, a hidden layer, which you don't know, but you set up, and an output layer. And the data goes into the input layer. So that might be an image or a sequence or some sort of numbers. And your predicted output, or what you would desire as the output, would go into the output layer. Now, everything in between, we don't know yet, but we set up each neuron to be connected to the other in terms of one layer to the other. And we work out the weights between the neurons. And these weights actually end up encompassing the way the problem is actually solved. Okay, so that's an important part of this, is that weights here is part of a training process. So we have an output result that we'd like, an input that goes in, and we can do this solution by running the network backwards to try to see what these values should be to give us back the input. And we actually use some calculus to do this. The details I won't share here, but basically various instances of the chain rule. If you make small changes here, what happens to the input into these weights? And you'll get a predicted output, which might not exactly be the result that you want. You have some error. And the objective is to optimize and to reduce the error as much as possible. This is called optimization. And if we can do this process, we can learn the weights, and the neural network will actually solve the problem. So why bother? Why are neural networks so important? Well, the first point is that they are powerful function approximators, which means a neural network can approximate any continuous function with arbitrary precision with just a single hidden layer. And there's some references there. It's a quite strong proof. That's been proven in many ways. But the gist of it is what we're interested in. And it basically maps the relationship between the input and output with little chunks. And each chunk, hopefully each chunk is less complicated. It turns out to be, in most cases, each chunk is less complicated, and each neuron handles each one of those chunks. And eventually you can learn to map the function arbitrarily accurately. Now, this is important not just mathematically. We're going to use this in case of imaging, because we may not necessarily understand one imaging aspect to another, but we can find the mapping, and that's incredibly powerful. And it's a nonlinear approximation, as we'll see on our next points. But the other important thing is that neural networks run quickly, because once we work out those weights we've talked about, they're essentially fixed. And to actually run the network, we don't have to do the training anymore. We simply just put the data in, and we get an answer output. And all of the stuff in between ends up being just matrix multiplications. Linear algebra, as you saw, it's a weighted sum, right? For each neuron. And that's what we do, and we compute that. And we can do that in parallel. And here we go. So these are all these connections between neurons. They're all weighted. And to compute anything, we just send our inputs in. All these matrix multiplications occur, and we get our output. And due to recent advancements in 3D gaming, where games try to render as much detail as possible in as many frames as possible, as fast as possible, you need to do it in parallel. So all of these graphical processing units, GPUs, actually have the capability to do large amounts of matrix multiplications very quickly in parallel. And there are open source frameworks that allow you to harness those technologies. And so what you get is the ability to basically run through these networks and train these networks really quickly. And that's what we talk about here, where we have highly parallelizable architectures. So basically, in a traditional computer, you have a CPU with a handful of cores, maybe 4, 8, 16, and memory. In a GPU, you have very large number of small threads, thousands, in fact. And you basically try to transfer as much information as possible, and you can do things in parallel. So here's an example of some 3D. This is a video. I might pass on a PDF of this so you can have a look at the videos itself. I won't run the videos today, but this basically frame shows you this sort of animated character in the early 2000s. But nowadays, we can run it at this level of detail with real-time lighting. And in fact, this is something called ray tracing. So we can actually map individual photons in light. And so there's a vast difference here is the number of parallel processes that we are able to use. And I talked about nonlinearity. So once you've done the weighted sum, how do you actually make the decision? How do you decide? Well, we use a nonlinear function to decide whether or not you should fire or activate. The neuron should activate or not. And there's a whole heap of them, and they all have advantages. The most famous one is here is ReLU, or the rectified linear unit. There's leaky ReLU, which is a slightly better version of ReLU. But the other versions that have been used before have been sigmoid, and then you have lots of other ones which are useful. Although it's nice to think of it this way, these days you just kind of do the machine learning dance. That kind of shows you the same sort of functions that we talk about. And here we can actually see the equations. They are all indeed nonlinear. My particular favorite one is the leaky ReLU. It's just a max between these two values that you get. And that maps us, allows us to make nonlinear mappings. And that's really important because majority of the time, the problems that we have are nonlinear. We don't understand everything that's involved between the mappings between A and B. And to do all of this, we need to solve it through optimization, as I said. So your network will give you a result, and we've changed it and adjusted the weights, but we do it small steps at a time. And as we do that, our final result isn't going to be the desired result, but close to it. And there'll be a small error. And that's called a loss, right? And here's an example of what all the errors of a loss function look like. So in other words, if we looked at the loss based on all the parameters everywhere, here's an example of a very simple problem, what a loss function might look like. And the objective is to obviously reduce the loss. And so it's equivalent to like having a ball roll down these plateau, or sorry, this sort of downhill process, and we try to optimize it. So we move the ball slowly towards the lowest point, which is the best result we can get for our neural network. And we do that by using the gradient of the slope, which ends up being this idea of gradient descent. So we descend down this slope. Depending on how we do it and what algorithm we use, you can sometimes end up with a local minima here. So that's not quite the best result, but it still gives us a result. Our neural network could actually, or optimizer might get stuck in those. But ideally, we want to find this global minimum. And that in itself is an area of research. But recent advancements in neural network optimizers means that this is less of a problem now, because we have some really nice optimizers. But that's the great thing. But this is the simplest way of doing optimization, gradient descent. We can use curvature, you can use all sorts of things, complicated things which slows things down. It turns out that neural networks can be optimized just by using simple gradient descent. And if you can map your problem to an optimization problem, you can basically map it to a neural network like this and optimize the solution out of it. So that's a very important and powerful idea. Okay, some of the other things that we can do is we can use data-driven approaches. So this means that instead of telling the neural network what it should be looking for, and in transferring our own biases to it, the learned networks can actually determine what is important out of the data itself, based on the data itself. Okay, so for example, if you're trying to identify dogs, different types of dogs, when training a neural network, you can actually learn to find the relevant features that correspond to different dog breeds, for example. And here is a hotspot showing where the neural network is actually looking at. So here's the image. But this is where the neural network is looking at. And obviously, it's looking at around the nose and the eyes to try to work out what these dog shapes or what the shape of their faces are, so to determine what sort of dog it is. I had a video here, but I'm not going to show the video, but basically you can see some of it here. We can work out all the different parts of where the neural network will have a look at in trying to work out whether this is an onion or not, or an apple. And here's some examples of where in the images it looks, and it determines this by the data itself. And here, this is another nice video, but again, I can't show, but we could walk around and this thing can run in real time, as we talked about, doing the parallel processing. And so the person here will walk around and the neural network decides and has a look, highlights areas, and then tells you what they are. Okay, so what are the other advantages over standard machine learning algorithms? Turns out that neural networks also get better when the data gets bigger. And this usually relates to issues like cursive dimensionality and other problems with conventional neural network, machine learning algorithms, is that the more data you add, the more confused it gets, and you don't really get much happening. Recent work has shown that in deep learning, which is sort of the neural networks, here the deep kind of relates to the more neurons you basically have, the more layers you have of neurons, the better it seems to perform, but the deeper it goes, the better it is. But basically, the more data you throw at it, the better it gets, and which is a remarkable thing, and which is really important in this day and age because we have so much data now. And finally, one of the important things is we saw that the neural network just takes the input and the output and works everything out in the middle. Previous ways to solve problems was to, here's the input, here's what I want as output, but I can't really get to the output, so I'm going to have to use some other surrogate measure. Maybe I'll have to register it, so use image alignment or registration. Maybe I need to use some other metric. Maybe I need to use some image processing algorithms. Maybe I need to use some statistics. I can't directly get to the output. But with a neural network, here's the input, here's the output, give me the best result. And because we're trying to work out the direct solution, we end up being usually not only faster, but more accurate, better performance. My experience is at least 15 to 20% better than anything we've done in the past. And I'll show you examples of those in this talk, in the second part of the talk more. And again, it's data driven. So all of these things are really cool, but there are some caveats, of course. All right. Artificial neural networks are computationally complex. So there is a lot of matrix multiplications. The more neurons you add, it grows exponentially. Okay, so it's not really suitable for small problems. And in fact, you saw from that graph previously, conventional machine learning algorithms are about similar. Training can take days, hours, weeks, and months sometimes. And again, that's due to feeding in more data, computational complexity, all of those issues. As I mentioned, traditional machine learning methods are just as good when the data is small. So, for example, random forest is actually quite a good tool to use when that's the case. Okay. Other things you should be aware of: neural networks can do linear regression, but they're simpler, better tools for that. So, for small problems, it's probably best to use traditional machine learning. But when you're going into big things, look at neural networks. Okay, so that's a basic rundown of why I think AI is a revolution, not a hype. Not just providing what looks like just better performance, but across the board, many advantages. So how do we use this in imaging? So firstly, what are images? You're probably familiar that it's made up of pixels. And the great thing about images is that the pixels have spatial correlation with their neighbors. And that means you have tons of algorithms, completely unrelated to machine learning and AI and deep learning. You have algorithms that use partial differential equations, edges, color, density, gradients, flow, you name it, texture. There are thousands of algorithms, tens of thousands. And it's a field on its own. It's image processing, the field. So what we want to do is to go beyond the low-level stuff and to understand images. Okay, but this is what it traditionally looks like, how to try to understand what images represent. The human has to do most of the steps. We need to know what to look for, so we have some idea of what we want to look at. Then we find the relevant features for that, for what we're trying to look at. And we need to have some way of extracting that. So we use an image processing algorithm. We need to work out the parameters. And then we hope that the algorithm that we've chosen, these handcrafted features, as it were, will give us good performance. And that's not always the case. And so you really rinse and repeat. You may need to replace your features. You may need to try again. And you keep turning these wheels until you end up having good results. In medical imaging, for example, what we've ended up getting in the past, it's taken years on the new. So if we're studying, say, the hip and the hip joint, the bones and the cartilage within it, it took me years to understand the data and the features required to get the good result. But what about what happens today? So this is our usual case. Here's deep learning, and here's the advantages we talked about. So artificial neural networks make it non-linear. It can learn the weights, parameterize the problem, and so designing new networks is actually a main driver of AI evolution. We'll see that later on. But this is the result. So I already mentioned 20 times faster, 20% more performance, but that's what we've experienced. You'll see that for some applications, it's even bigger. We've seen it directly solve the problem, and we use open source frameworks. Excuse me. And here are those GPUs that come in again to help out. So the biggest breakthrough we had was in 2012. There's a challenge that runs to classify images. So is it a car? Is it a dog? Is it a cat? And it's called the Sci-Fi 10 and the Sci-Fi 100 data set. And basically, either it has 10 categories or 100 categories. How successful can your algorithm classify those images? And so the first use of a convolutional neural network, and we'll talk about that soon, it determined all of the image features. Here we go. These are all the basis functions that it's determined itself, data-driven, to try to make the best classification performance possible. And it completely destroyed the opposition for the first time. And it was based on purely data-driven approaches and using something called convolutions, which we'll talk about soon. And this was quite a revolution back in the day. So down here, right in 2012, the performance is around 50%. So half the time you're wrong, the computer. So not very useful. Suddenly, in 2013, this AlexNet was, around 64% accurate, which still isn't great, but a big improvement. And this algorithms were stuck here for almost a decade around here. Suddenly, this convolutional neural network took off, and then it's been absolutely crazy since then. To point out, roughly, this is equivalent to human level performance. So a human is actually, in the 90% accurate in how well they categorize some of these images. Anyway, these neural networks can match human level performance. And you can see the average now for all of these networks. Every one of these dots is an algorithm released these days with code from this nice site here, and it's doing quite well. So the concept used in these networks, not only is it a neural network, but each neighboring, all the neighbors are accounted for using this idea of convolution. And a convolution is simply a weighted sum of neighbors, you could say, have a look at, or filter, you can imagine. That, for example, if you did something like this, you apply these weights, and this is the kernel. So a CNN will actually try to determine what this optimal kernel is. So it starts out with a random kernel, and will work out the optimal kernels, but it will go through and do the weighted sums of these to produce these results, and then put them into the output like this. And it's a sliding window, basically. It's done in parallel processing using the GPUs, and it's basically a way of processing a window across, or neighbors, or the spatial relationship between pixels, capture the spatial relationship between pixels. So these convolutional neural networks have revolutionized the imaging field. They perform feature extraction, and they learn these filters. So these filters, kernel filters here, excuse me, these are learned. So instead of humans trying to determine what the best filters are, like I mentioned, do you use edges, do you use textures, do you apply PDEs? These kernels are learned. And so it's data driven. So earlier layer will extract fine grained details, deeper layers extract more higher level details. And we'll see why. So why does this kind of work? Is why would a neighborhood or a filter make sense? And it's this idea of receptive fields. So it turns out when you look at macaws, so that's sort of like a monkey, their visual cortex, what their model field looks like, trying to understand images using Gabor filters looks like this. These are the actual filters that they've measured from the visual cortex of these monkeys. And they are very similar to something called Gabor filters, and you'll see like these things here. And they are basically these types of filters we talked about. And if we go back to AlexNet, you can see the things that it's automatically determined from the data. So it's sort of already beginning to mimic a mammalian visual system. And that's a great advantage that it's found. And so here's an example of a receptive field. If you have an image A, you apply some of these Gabor filters, this is sort of what you get. And the great thing about this is, it's highlighting the important parts in the image. So where things don't change, you really don't need to concentrate too much on that. But where you have like texture and things, and you can see the curves, you can sort of use that to identify what's going on in images. So, and those are convolutional neural networks. They mimic the human vision system. And here's sort of a basic structure of what a convolutional neural network would look like to do some classification, to decide what an image is. So you'd start out with an input, and then you do some convolutions. And these will give you some what's called feature maps. So every filter produces a feature map. So if we go back, this is sort of like a feature map here. B uses like a feature map. And then we want to increase the receptive field. So we want to make those functions bigger. And one way to do that is to subsample those images and repeat the process with convolutions. And that way you increase your receptive field on the object you're looking at. And this is the process that we go about: subsample, convolution, subsample, convolution. And then you have a normal neural network that we talked about that's fully connected together, just like in like our third or fourth slide. And the output is the category that we want to obtain. So here's a diagrammatic example that NVIDIA has used. So you can check it out at one of those links. But basically, you know, you have a face that goes in. These neural networks are not connected to every other network, but just to the local neighborhoods. And you do this convolution and subsampling, convolution, subsampling, blah, blah, blah. Up to here, we have the normal neural network, and that decides that it's Sarah. And in the process of training, the neural network itself learns these filters itself. And at later stages, because we're enlarging our receptive field, we're looking at larger portions of the image. So we start looking at noses and eyes, and then we start looking at faces and whatnot. And this is what's been observed in other papers as well. So another one of the NVIDIA's papers, when they look at different data sets, they can see, you know, parts of cars, parts of faces, the elephant tusks, the chairs, and bits of motorbikes and things. And so what is this subsampling part? And usually it's a very simple operation. We basically take the max. So here's what it shows. You take a big square, you divide it up, and then you just decide whichever pixel is the max. So it's sort of like looking at the biggest values, like looking at hopefully what's the most important thing in the image. And you do that over here, you subsample and you do convolutions. And notice that I've got a number of feature maps here. So I have to decide how many filters I'm going to learn, which end up being the number of feature maps that I want. And that's sort of a parameter of the neural network. So the more number of these layers there are, the more deeper the network is. Okay, and then some of the math is just basically matrix multiplication when you have a filter and you're applying this convolution. Okay, so the desired task is to simulate the receptive fields at each of these levels, and we apply them to determine and learn the feature map. Okay, and finally, to really understand how these networks work and how we get the desired results we want, especially in tasks that I usually do, which involves segmentation. Segmentation is sort of like determining what categories different parts of the image fall under. So where is the bone, where is the muscles, and all of that in an MRI, and I'll get to that later. But how do we sort of encode an image? And the idea comes from something called an autoencoder. And if there's one thing that you take out of these slides is hopefully I can explain what an autoencoder is, and it's a very powerful idea. And the idea is that you have this information bottleneck. Now you can see that each block here probably represents a value. So this might be your input. And at every subsequent layer, the number of values that we have is decreasing. So it goes through this reduction up to these only 3 values now, and then goes back out to the same number of values as the input. Now, in order for this neural network to succeed in what it does, and that is to recover the output from the input, going through an information bottleneck where everything is reduced and then pushed back up, you end up with a compression. You end up with this internal representation here, which is a compression of the input. Now, it's a compression in the information sense, because if you just ignore this half, the first half, the encoder, if I give you the code that's learned in the middle, it should recover the output. So this here learns something very important about your input image in order for it to recover. And that's the idea of an autoencoder. And a key innovation in segmentation is this idea of the U-Net, where you basically have the same process, but you have these sort of skip connections across these layers that just join these layers to ensure that any high resolution information is not lost. Because as you're going up this way, you may learn something about the image, but the high frequency information or the high resolution information not related to the code itself, but just to recover a high quality image that's not blurred requires some of the information that's lost, and these skip connections allow you to do that, and that forms the base of the UNet, and I'll talk about that more. And so this paper here, these guys in Europe, they just discovered this property where they have these skip connections in gray, and they do these convolutions, and the red arrow here is a downsample, and then they can upsample, and then they get that segmentation. And this is an example of a segmentation. So here's an input, and here's what they want. And they want every cell here to be identified for what it is. And this works very well. Okay, and we'll talk about the UNet a little later in the last part of the talk. And lastly, one of the most important and interesting ideas related to the face that you saw in the earlier slides, how someone could possibly generate a fake face that realistic, is using the idea of generative models. So here's a data set that's well known. It's called the MNIST data set. I'm sure if you've done machine learning, you've seen some of it. You have these digits, and they're handwritten digits, and these are just some examples of some of these digits. The question is, can you learn a manifold? In other words, can you learn some sort of probability distribution or image distribution? You might think of it as like a cloud of data, and everything is linked together, but similar examples. So maybe 5s will be together because they look similar. 1s are sort of out here because they look similar. But as you go from 1s to 5s, there's a transformation happening, and it's a continuous space, this cloud or surface. I like to think of it as a higher dimensional surface, a manifold, as it were. And a manifold is just a higher dimensional surface. So you might think of if you fold the paper out like this, it forms a surface, and you distribute your image across this. And any image on those surface, you can sort of interpolate between them. And if you apply this to the MNIST data set, and you can have a look at this, you can just Google Keras building autoencoders. You can create these manifolds. And here's a manifold, it's a square one. And you can see that 0s sort of morph into 3s, then morph out into 1s, and 1s turn into 7s, 7s turn into 9s, and 0s, etc. And so you can learn these things. And these generative models are able to learn these manifolds. Now, I wanted to quickly describe what a generative adversarial network is, the GAN that's responsible for the face. It's a little hard to describe in just one slide in a couple of seconds, but the main idea is that you got to think of it, instead of having a single network, you have 2 networks that work against each other to try to trick, well, one of them tries to trick the other, while the other tries to catch the other one in the act. And this adversarial learning means that both networks can help each other understand the problem and help what the generator is, the counterfeiter, to generate realistic images. And in order to do that, to learn realistic images, it actually has to understand the distribution of the images, so the manifold. And the result is the generator is learning the manifold, and the discriminator is this other network that basically makes a classification between a fake image and a real image and decides whether it's fake or not. And once the discriminator, which is a network, could be any type of network, can't tell the difference between a real and a fake, then that means the generator is then fully trained, ready to encompass your model. And that's the general idea of how a generative adversarial network works. The one used to learn the face has an extra bit here to the latent space where it's mapped to a style. And that style is something that allows you to really map the manifold in a better way than what is traditionally done in a GAN. But the main idea is, as I said, you can have multiple networks interrogating and checking each other to help improve performance. Okay, One of the other key ideas that we now have in imaging is this idea of neural architecture search. So remember how I said someone came up with the UNet? So they came up with this UNet, and you have these skip connections, and allows it to do allowed it to do the segmentation or the results that you want. So the key question is, how do you know when to downsample? How do you know when to upsample? What is the optimal combination? When do you pool? When do you not pool? When do you do convolutions? And when do you subsample? And the idea of a neural architecture search is, well, let the network decide. Let's build almost every possible combination. And note that it's not every possible combination, but a good example of. So you build this trellis shape, and every arrow here is sort of either, if it's going down that way, it's a down sample. If it's going up, it's an up sample. If it's going across, there's no change in resolution. And the idea is to try to find the best UNet structure. And that's the one that they found. Oh, sorry, that's the one that they found empirically when they designed a previous work called Deep Lab. So, just with handcrafting brute force, they found that this one worked the best. This is sort of similar to the UNet. And this is the one that you use from the stacked hourglass. If we go back, I'm not sure if I've got the original one. No, I haven't got the original one, but it's kind of a combination of these two. The one that they find works best. So that's the next stage is, instead of humans designing these neural network architectures, let's have the whole process, the data-driven process, design itself. And that's a really exciting area that we've been working on, and I'll talk to you about soon. Just before I finish off the imaging section, and hopefully we're not running too fast on time. Yeah, we're doing okay. The next big thing are these things called transformers. So I mentioned in neural networks, those weights are fixed. Well, now transformers allow you to have weights that vary depending on the input, so-called self-attention. And this is a big thing because it generalizes the neural network I showed to you on the second or third slide. And this means you can do all sorts of things, more general than what we've been able to do before. And right now, this is being applied to natural language processing. But here, as we see, if you'd like to see this explanation of that work, it's called Visual Transformers. This is a video by Yannick Kitchler on YouTube. And if you just, images worth 16 by 16 words, or attention is all you need. If you search that, you'll be able to find his videos, and they explain how all of these networks work. But basically, these transformers may point out that we no longer need convolutions because the neural networks can learn if convolutions are needed. So, we have that bias that convolutions should be needed to represent visual cortex. Well, transformers go beyond that and say, well, we'll use a convolution if we need it. So another great, interesting work. That's probably what we'll look at next in our research. But anyway, so where do I fit in? Now, hopefully that gives you an overview of all the terms that I'll need when I'll discuss the works. But this is what we're trying to do. So there's various diseases that relate to the human body. We are looking at osteoarthritis. So that's basically related to your cartilage and bone in all your joints. And when you move your joints around, there are cartilage or articular cartilages that act as shock absorbers. Over time, they get damaged and wear out. But if you have an injury, you might lose it completely. And that can result in a lot of pain and damage to the bones, and that's called osteoarthritis. And so what we want to see in medical imaging is, we don't want to operate on them, open up patients and look inside the knee. We can use MRI to look inside the knee non-invasively. So in the middle here, I've got a scan over MRI scan of the knee. Now this is looking side on, so sort of side on to the body, as it were, from from this side, I guess, at the knee. And if you can see my cursor, here's the kneecap, here's your thigh bone or your femoral bone, and here's your tibia or your shin bone, I guess you could say. And all of these other things are muscles. And what MRI does is it basically looks at the density of hydrogen atoms within the scanning area. And the lighter it is, although there's some details here that I'm not explaining, but the lighter it is, the more fluid there is. There's more water there. There's more hydrogen there. And so we can see the knee, and we can see the cartilages, these little thin structures between the bones. Not sure if this, sorry, were they playing? I didn't notice if they were playing. Yeah, they're playing. So here's a knee. There are 3 different types of knees here, or 3 different representations. What we've done is we've tried to build a machine learning model using traditional machine learning to try to learn knee bone shape. So here's lots of different shapes and how they change, how the model changes across populations. So if I go back and show you again, some of the variations we see is that we get thinner knees, the thinner femoral bones, which is the thigh bone. We get more different shapes for the tibia bone. The patella moves around. Not sure if that actually animates. So you can see the patella moving, which is your kneecap, moving up and down. And we've used machine learning of bone shape to try to quantify what the shape looks like using triangulated surfaces and PCA. I'll talk about that. But the idea is we acquire this knee MRI, we apply our algorithms to work out where the bone and cartilage is. And in MRI, not only can we just look at the hydrogen atoms, we can look at how water is, where the water is, where glycosaminoglycans or amino proteins and other things that involve hydrogens, where they are. These are called biochemical images. And we can extract both to build up this picture of how healthy the cartilage is and use that for early detection of osteoarthritis. So we want to study disease using these algorithms. Okay, but here's the main problem. All right, we're actually now living in an age where there is so much data that we can't process it in meaningful time. And that leads to very hard decisions about what to image and what not to image. And it turns out, because MRIs consist of hundreds of 2-dimensional images to make up a 3D picture of a knee, it takes an expert, someone who knows knees, someone like a radiologist who looks at MRI, several hours to process these. And just for numbers, a patient might have several of these scans and might have few visits. So 7 scans and 3 visits. And maybe now you're trying to understand osteoarthritis, so you have to look at 1,000 patients. So if we put all of that together and it takes 3 hours per patient, we're looking at 7 years of processing. Now, I'll show you models that would now run in 3 seconds rather than several hours, and it would take less than a day to process that time. And that's so important. We can now study large number of patients. Our MRI is our best visual representation of a knee and its health that's available, save doing a surgery. And so now we can have networks that can actually analyze these things in massive numbers. And there's already been work shown that we can actually use a network once we've done the processing and pulled out all the segmentations. Well, they don't do it for segmentations, but they just look at brains to try to see how well MRI quality, image quality compares, but you can have a network that looks at all of the data at once, which is something that would take a human almost a lifetime to do. So how do we do this? We use principal component analysis. Some of you may know about this, but basically we put all of our, we have a triangulated surface for each shape. We put the positions of these into a covariance matrix and do the eigen decomposition. And this basically pulls out the biggest variations in position, normalized position that is, of various parts of the surface which correspond to shape. So if we vary the shape here, you can see that people, this is the prostate, by the way. It's not intuitive to most people what prostates look like, but it's a big blob, but it can have various sizes and depending on treatment. So the model allows us to model those changes. And hopefully you can see some of the things happening here. We have the femur. So here's your hip joint. This is your pelvis and the socket where the hip joint connects. And most people have different sizes for these sockets, which makes sense. You can see big size to small size. And of course, yeah, this is the part of the shoulder blade, and everybody's shoulder has different sizes and different angles in the way they are positioned. Okay, so we can build these models out of PCA. And once we build the models, our algorithms try to find those shapes in MRI. And here the 3D MRI is represented by a single slice. The dark images there represent the hip bones. And this algorithm searches, is searching for the pelvis, and eventually it will search for the femur as well. Here we go. And all the while it's making sure that this shape model is making sure that the surface looks like what a hip would actually should be anatomically correct. And that's what we use it for. Now, what I've done is improve the PCA by using spatially weighted PCA. There's robust PCAs. And with that, basically, we can target the cartilage area. We can tell the machine learning algorithm, spend all of your energy trying to learn in the area that's most important to us, which is the cartilage area. And because of that, we get more accurate results. So the robust is what is being currently used, but we can use this focused, this idea of this spatially weighted PCA, which is focusing on the area we want, is more accurate in segmentation results. And here's an example of it in play. Red indicates very high weights. So we want where the joint is to be more accurate than out here where we don't really care about how accurate it is. But basically it'll run through and find the pelvis, make sure it's aligned properly, and give us a nice, again, the MRI is represented as a 2D slice there, but there's all 3D information around it. And we've done this to find multiple objects. So here's the pelvic region. We have the bone. Here's the bone, the body outline, the prostate, the bladder, the rectum. The bladder is this white, bright thing. The data is in 3D, but we show one slice. And if we run that through, our algorithm actually actively finds this. And we turn on and off objects hierarchically to improve performance in detecting smaller objects. So we solve the problem of multi-object segmentation through using these spatially weighted PCA models. And you can see finally we just go to the prostate, and it's quite accurate. So what we're doing now, if we have enough time, is now we're looking to improve upon these unit ideas. And the unit, as I've indicated before, kind of takes this image, downsamples it, determines more feature maps, downsamples it, more feature maps, etc., gets this code and then reconstructs it and has these skip connections to ensure that no data is lost. And so it'll learn everything about all of the images being processed. And the pooling process is quite simple. We end up with a question. Oh, okay. So how many manual segmentations are we using? So that's one of the limitations as well with medical imaging. Usually, as I said, it takes several hours. So we only have hundreds of them. And so we have to use things like data augmentation and other techniques to try to simulate more data than we have to try to sort these problems out. So that's one of the limitations we have. And that's where GANs also come in to help with try to understand the data better so we can do better augmentation. But getting back to the unit, when we do this segmentation, the unit makes sure that we don't lose any information. Now, if you remember correctly, this process was really good for when we did classification, because once we got to this point, all we needed to do was then run it through a classifier. Now, do we really need to do this downsampling and upsampling business? So if I go back to that. And this is just showing how the up convolution works, but really we use it to increase our resolution and try to recover what's been lost. Doesn't work very well for 3D data. And the idea that we came up with, we didn't come up with, sorry, for 2D photographs, the guys in the US, they came up with that you don't actually need to do downsampling. We're just trying to increase the receptive field, and there's other ways to do that, and using something called dilated convolutions. Unfortunately, we don't have time to go through the details of that, but just know that there's ways to do it without downsampling. Oh, by the way, these are some of the results we can get with the unit. Here's a brain MRI, and we'd like to segment, say, the white matter here. The right-hand side shows what the actual segmentation should look like. Here's our result. And these are the things that the neural network feature maps look like. So it's determining filters that extract these particular white matter areas. And they're all different, you might say, derivatives of the white matter, and trying to determine what filters work best. And you can also do that for a lot more labels like this, and you get lots of different filters. But what we've done is we've used something called context aggregation, and that's dilated convolutions. You can replace this shortcut once and replace the whole unit inside with this context aggregation, and you can outperform everything. So you have UNet, 3D unit, another 3D unit, you got the VNet, and the CAN 3D that we recently accepted, does outperform everything. And the bonus is, if we do 3D processing, we get these really nice. So usually these networks ignore lesions like these. These are injuries that shouldn't be there, but these knees have injuries on them. Other networks miss them. Our work kind of identifies them, and that's the next exciting thing we're looking at. We've got another comment. Yeah, I'm almost done. I'm almost done. So that's sort of what we've done in the segmentation space. But remember, we talked about neural architecture search. So we've also been looking at that. Again, replacing the UNet inside it completely, because we don't know how many downsamples and upsamples and who knows what we need. We just build a fabric, which is basically very similar to the trellis that we showed before, but except instead of finding the best one, we use every possible combination. And this is an interconnected web of all possible up and down samples. And it kind of looks like this. So at every scale, we sort of interconnect everything, and we work the best solution out. And it turns out it works great even in 3D, and it's possible in 3D. And each cell consists of a different scale dilated. In here, we've got some dilated convolutions here. We use dilated convolutions to inspect the volumes at each scale. And lastly, the final thing we want to look at is these gang things. So we want to learn the manifold of MRI scans. So we do the crazy thing of doing the opposite of segmentation. Segmentation is you are given this MRI over here, and you try to identify, oh, here's the bone, here's the bladder, here's the muscles, here's the prostate, etc. Well, if we can take the segmentation like this and create an image out of it, then we're going to understand the tissues and the appearances of those particular tissues, objects that we're interested in. And that's exactly what we've done. So we've built this network, which effectively creates a conditional StyleGAN2, which takes in segmentation and produces a unique MRI out of it. So in other words, if I gave you, told you where the eyes, nose, and cheeks are without showing you a face, but just telling you where things are, I can generate a face, a realistic face out of it. And here, what we've done for MR. And interestingly enough, we've cross-trained it so it also can generate a CT scan. CT scan is made up of X-rays, so you mostly see only bone, some tissue, because X-rays go straight through tissue, and bone absorbs them well, so you get white stuff. But that's basically it. And these are some of the cool results. Here's what it should look like. Here's what the generated MR looks like. And you can see it's pretty good correlation, and the same goes for the CT scan. And that allows us to basically build a manifold out of this. And you can use machine learning tools like the UMAP to map that manifold, and we've done that. So you can have a look and create this high dimensional surface, use UMAP to flatten it out onto a 2D plane, and then interrogate it and walk along the path, and you'll see that it, like changing and morphing a face from one to the other, we can change and morph an MRI like that. And again, there's a link there to the paper if you're interested, but this is all the cool stuff that's going on about. So just to conclude, sorry, I've gone a few minutes over. It's the neural networks that are driving the AI revolution. And we can now create nonlinear algorithms that outperform conventional algorithms, runs in near real time, not limited by large data, and can be solved by gradient descent. So it's massive. And CNNs are really great because they improve these sorts of things for images. And what we're trying to do is do fully automatic 3D segmentation. It's really quick, so we can do large studies. We can add multiple data sets, and we can basically try to create AI systems for medical imaging for the future. All right, thank you very much. That's me. Thank you very much.
All right. If anyone has any questions, this is the time to ask them. If not, I'd just like to thank Shakes for giving up his time, especially giving us such an insightful lecture on how AI is actually used in practically. Secondly, we have an event next week as well, guys. It'll be on Tuesday, and it's actually with MSS. So feel free to tune into that as well. It'll be an in-person event this time, though. There'll be free pizza as well, though. So that's an extra incentive for you guys to come. And that's pretty much it. All right, thanks so much for coming, guys.
Thanks, we'll catch you later. I can stay on for a little bit to answer some questions if some of you are interested. So Hunter asks, what do you recommend we next do to engage in this field? So I presume you would like to do some stuff in the area, do some research, and have a go at it yourself. So the MNIST data set, the sci-fi data sets, those are all available. So in terms of just the AI and the imaging, you can go ahead and do those things. There's plenty of tutorials. In terms of the MRI, segmentation, brain, and all those, there are actually I'm offering winter and summer scholarships, but I have colleagues that do the same. CSIRO have summer and winter scholarships. There are thesis projects as well that you can get involved in. So there's some opportunities. In terms of courses, as I said, there's Comp 3710, which we go through all of these in more detail, and you have an opportunity to, I provide data sets where you can crunch away. So that's if you'd like to take the course. But also, I usually run Summer of AI across the summer. Last summer, we ran it over 10 weeks or so, which was probably a bit long. We might condense that into a fortnight or something like that, and then just try to run through GANs and VAEs and all those sorts of things. So look out for the Summer of AI and other things. Cool.